Now we'll start a new section, and that is on box culverts. Can you hear me?
Yes, sir.
Right, okay. So box culverts have certain advantages, and box culverts can be used instead of bridges where the damage due to covering is not very significant. So if there's a chance that the covering can occur, like in a large river where you are not sure of the type of flow, then box culverts are not good. But if you are sure that the flow is not going to cause a lot of covering, then box culverts can be used, and there are few advantages. And also these days box culverts are used a lot when we construct the motorway expressways. When you are constructing expressways, still we have to allow people to go through the expressway. For that, box culverts can be used. So the advantage is the box culvert is a rigid frame structure where both horizontal and vertical members are made with solid slab, and hence it's relatively easy to construct. That's one. And because it's a rigid structure, then slabs can be optimized because all the slabs will behave as continuous slabs. So in the case of high embankments, if you just try to have a bridge, then you will find that the embankments are the piers are very tall. But in the case of box culvert, you can just construct the box culvert to the height that you need, and above that, you can just go for the soil fill. And so they are also particularly suitable for places where the scouring is not there. And economical solution for expressway when expressways cross other roads. And the other advantage is, we have a slab at the bottom, and that slab can act as a raft and distribute all the loads from the box culvert onto a large area. So those are the advantages of box culverts. So we see what are the load cases that we have to consider. So in the case of box culverts, we are having some soil fill here. And if the soil fill, sometimes you can have even 2-3 meters of soil fill above the box culvert. In such situations, sometimes you will get slightly higher loads than the load directly above, and that occurs due to some arching action that can occur in the soils. So when you are designing box culverts, if the soil is thick, then we'll go for this arching action. And when we have say 1 meter of soil fill, we actually consider it can actually increase by about 15% because of these various arching actions that can occur within the soil. So when you are designing, we have to actually consider an additional beta factor for the weight of the soil that is acting above. So now when you have a box culvert, you can have various load cases. So basically what happens is, so when you have a box culvert, like this. It is supported here by the soil, and then we get various live loads acting above, and we also get soil pressure thing on the box culvert. In addition to that, we might have vehicles above, so that will give rise to a surcharge. So you get a surcharge. So when you have so many different loads that are acting on the box culvert, surcharge is load like that. Then you have loads here. On this side also you can get those loads. From here you get these loads. So there are so many different types of loads acting on the structure. So this can lead to so many different combinations. One possibility is that the box culvert is loaded fully here, and this soil pressure is something that we assume might not act in the same intensity. So in such a situation, the box culvert will behave like this. And then it will go on like that. On the other hand, there's a possibility that the maximum soil pressure is acting, but we don't have any live load here. So in such a situation, we might get something like this. In reality, it will not lift up like this, but this shows the possibility. When this deform this way, this can deform that way. So when you are designing, we have to consider all these different combinations. And when the soil properties are known, you can design it for active pressure, soil pressure at rest, where K is given by 1 minus sine phi. 1 minus sine phi, and you will not design it for active pressure, because for active pressure to develop, the wall has to move this way. This wall has to move. But in a box culvert, the wall cannot move. So because of that, we design for the soil at rest condition. Soil at rest condition. So soil at rest condition, the lateral, the soil pressure, the K value for soil pressure is given by 1 minus sine phi. And if phi is 30, 1 minus sine phi will give 0.5. But if you do not know the phi value, generally we use a factor like 0.6. If you do not have any exact idea about the value of this angle, friction angle, then we generally use a value like 0.6. So the important things are the additional load from above, and then when you have so many different loads acting, then we have to consider various load factors, and the load factors used are at ultimate limit state for concrete structures 1.15, and for superimposed loads at ultimate limit state, the value of 1.75 is used because sometimes you find that without removing the carpet, we might lay a carpet on top of existing one. So in that case, the superimposed pavement construction load can have a higher factor of safety. And then you can get horizontal soil pressures earth pressures and hydrostatic pressure. Then you will get live load factors. If you are considering only the HA loading, A-type loading, the uniformly distributed loading, then the factor is 1.5. But if you are considering the special heavy loads like B-type loading, then the factor of safety is lesser, 1.3. And for cycle tracks and footway, 1.5. So there are some factors associated with it. And then in that case, you have to consider load case 1. And load case 3 is for temperature effects. Load case 4 is for the effect of the HA-HB loads with the break-in loads or traction loads. Break-in loads or the traction loads. So basically, when the vehicles apply brakes on top of a highway structure, part of that break-in load will actually be transferred onto the structure that you are designing. So all those can be considered. And on top of all these factors, we have another factor called gamma F3. So if you look at the live loads due to HB loading, the overall factor of safety will not be 1.3. That will be 1.3 multiplied by gamma F3. And the gamma F3 value is generally taken as 1.15. Generally taken as 1.15. And this is an additional factor to take account of inaccuracies of the loads evaluated. So we have an additional factor. Yeah. Yes.
Sir, we can't see the screen.
You can't see the screen?
Yes.
How could that be? I haven't shared the screen. Can you share the screen now?
Yes, sir. Now okay, sir.
Yeah, so basically there are factors called, due to the permanent loads, you get various factors. And there are combination 1, combination 2, combination 3, combination 4. Combination 2 is for wind loads, which is not applicable for box culverts. Combination 3 for temperature loads and combination 4 for braking loads and all that. Combination 1 for all the live load, data and live loads. And there are factors like, A-type loading 1.5, B-type loading 1.3. And then on top of all that, you have another factor called gamma F3, which is 1.15. So then, to take account of all these effects, we can consider different load combinations. And here you can see this is the pavement, and a factor of 1.75 can be used. And gamma F3 is 1.1. And sorry, gamma F3 is 1.1, not 1.15, 1.1. So you can use a gamma F3 of 1.1. And in addition to that, you can have a beta factor. And the beta factor is 1.15, and that is to take account of various arching action induced additional forces. So when the soil spans over certain length, sometimes arching action can develop and it can lead to some additional forces. So 1.15 is the value for beta, and gamma F3 is 1.1. And in addition to that, you have to consider the weight of the structure, which is considered as 1.15, and that comes from this table. Here you can see for concrete, weight of concrete, we use a factor of safety of 1.15. And in addition to that, we can get earth pressure acting on it, earth pressure. And for the earth pressure calculation, we use K as 0.6. And that is, considering that, earth is at rest, and gamma FL, that is the load factor, is 1.5. Gamma F3 is 1.1. On the other hand, you can actually calculate it using the, the coefficients given in BS for soil parameters if the soil parameters are known. And for the live load surcharge, also we can use the same factors. If you are using this, use the same values for live load surcharge. On the other hand, you know soil parameters properly. You can calculate the value of K, then use the calculated value. But most of the time, because we don't have exact information on the type of soil fill they do and how much they compact and so on, what we generally do is we use a factor like these factors. And then, you can get the soil pressure acting from both sides, from this side and also from this side. So you can get the forces acting from both sides and forces from above. So you can create the load combinations. And then the next important question that you can ask is, how you are going to deal with the foundation. And we can actually deal with the foundation by considering that it all going to be on springs. And we can actually apply set of springs here and then do the analysis. So then, so this is the maximum load case. Everything is maximum. All the loads are at the maximum values. Then comes the other variations. Other variations are, this is maximum, these are minimum. These are minimum, but this is maximum. The other possibilities, these are minimum, that means no live load, and all these factors we remove. These are minimum, but these are maximum. So those are variations that you can consider. So basically, you have to consider another case where no live load, but there can be vehicles here, so you get superimposed the surcharge all acting, and these are maximum. And here also you can see all these values. The beta also we consider as 1, and all these parameters we consider as 1. And then there's another possibility that these are all maximum, but no surcharge. All the loads are here. And then you will get, we consider that because these are maximum values, these are maximum, we consider these to be the minimum. That means no surcharge, and we consider the minimum value for lateral soil pressure, which is considered as with a factor of 0.2. So generally, to calculate the maximum, we use the soil pressure coefficient of 0.6, but to find the minimum, we use a soil pressure coefficient of 0.2. And then you get another situation where the break-in loads are also acting. So when the break-in loads are acting, you will get some pressure developing on this side. And we consider that the full pressure is developed there. But here you will get a reduction in pressure because the break-in load is acting that way. So you can get a reduction in pressure. And surcharge also you get a reduction. So there are 4 cases. And so this is break-in load with maximum load. And you can get break-in load with minimum value here. So that's also another possibility. So those are the various loading possibilities you have to consider when you are designing a box culvert. In addition to that, one of the other important thing is, these box culverts will be provided with haunches. The idea of providing a haunch or a thickened section here is to ensure that, the joint can carry a bigger moment so that no cracks will develop in this area. The reason is this type of haunch will allow us to provide diagonal bars that can actually prevent any adverse behavior. So in addition to that, we have to consider the type of loading. Now, I have used 1978 loading, but later, RDA started using BS 5400 2006 loading also. But because I just want to highlight the type of loading that will act. So I have considered these earlier loads which are lower than the loads that are used at the moment. But so if you look at Eurocode loads also consist of this kind of uniformly distributed load. But in addition to the uniformly distributed load, along with uniformly distributed load, they actually specify two more axles. Whereas in the earlier British code, they defined something called knife edge load that went along with the, the UDL loading, and the knife edge load magnitude is 120 kilonewtons, kilonewton load acting across the lane. So it's a 12-ton, 120 kilonewton or 12-ton load acting across the lane, and only at one location in the lane it will act, and the rest will be the UDL, and the UDL is given per lane, and in the earlier British standards they allow the lane width to vary from something like 2.8 meters to 2.6 meters to 2.6 or 2.7 meters to a value like 3.8 meters. In a moment, I'll show you the table. But in Eurocodes, you'll find it's different. Eurocodes is different. So this is the B-type loading. But before that, I'll come to this loading. Here you can see the loading width can vary from 4.6 meters to 7.6. That means the width of the lane can vary from 2.3 meters to 3.8 meters. But whereas in the Eurocodes, the lane width is limited to 3 meters. So lane width is 3 meters. So if you have a road having a width of say 7 meters, then you will consider it can have one 3-meter lane, another 3-meter lane, and another portion which is 1 meter wide. So that's how they consider the number of lanes. Whereas in the British standard, if you have a width of 7 meters, you have considered only 2 lanes. Whereas in the Eurocode, it's slightly different. They have fixed lane width, which is 3 meters. So this will not affect us very much because we are dealing with box culverts. And then in addition to that, they define something called B-type loading. B-type loading is, one axle, one unit of B-type loading is 1 ton per axle. 1 ton per axle. So it is 1 ton, another 1 ton. So altogether 4 tons. One HB unit means 4 tons. So generally the bridges are designed for 30 units of HP or 45 units of HP depending on the type of road. All the main roads, the expressways, they are all designed for 45 units of HP, whereas the normal smaller roads, not the trunk roads like A-type roads, but sometimes B and C-type roads. So if you think that the chances of very heavy loads being taken is remote, then you can design those for 30 units of HP, which will give a vehicle weight of 120 tons, So in addition to that, so when you say 1 ton per axle, each wheel will carry 0.25 tons or 25 kilonewtons. So basically, when you are designing for 30 units of HB, then each wheel will have 75 kilonewtons of load. So you can see now these loads are located close by and we have a soil field. So within the soil field, these loads will distribute and the distribution is 2 vertical, 1 horizontal. 2 vertical, 1 horizontal. And if the soil field is high, then there's a chance that these loads will overlap. And if the loads are overlapping, what we do is we calculate these two loads, this load and this load, and then add them up and divide it by this width. And here we are not going to say, because of overlapping, you are going to get a higher stress here. We are not going to say because of overlapping, you are going to end up with a higher stress there. So, and in addition to that, you have to consider the situation where the lane is located, the load is located close to the edge of the box culvert. So the box culvert ends here and you are going to get a parapet wall here. So that means, there's no way you can distribute the load here because there's no concrete here, it's air. So you have to stop distributing. So that also should be paid some attention when you are placing the loads. So those are the important things that you have to consider. And so for 1 unit of HV loading, each axle carries 1 ton or 10 kilonewtons. So each wheel will carry 2.5 kilonewtons. For 30 units, each wheel will carry 75 kilonewtons. And then you will ask, if there are point loads like this, what is the contact area? The contact area is the stress is limited to 1.1 newtons per millimeter squared. So that gives a contact area of 261 millimeter by 261 millimeter for a load of 75 kilonewtons, because we have to keep the load, we have to keep the stress at a maximum value of 1.1 newtons per millimeter squared. So in addition to that, you have to consider if there are cycle tracks and so on, those loads also should be considered, but they are not very high. The cycle track loading is about 5 kilonewtons per meter squared. So these are the loads. And then, if the soil fill is more than 0.6 meters, then it is stated that you have to consider only this loading. Because if the fill is thick, for UDS you get considerable distribution, and because of that reason, if the fill is thick, then we use only this type of loading. So if the fill height is more than 0.6 meters, we have to consider only this B type loading. So in addition to that, now we have to think about the foundation. The foundation is part of the box culvert, and that is the bottom slab. And the bottom slab is acting like a raft. So because of that, generally we use a thicker slab for bottom, because it's loaded by 2 walls on the edge, which are almost like rigid walls. And then all the soil pressure will act in the middle. So because of that, this bottom slab can bend upwards. So you have to have sufficient thickness to make sure that these bending stresses are kept at a lower level. So because of that reason, generally the bottom slab thickness can be higher than the top slab thickness. So how do you actually apply a soil spring? And as you have seen with horizontal springs, the vertical springs, the equation is simple, because this vertical stress actually correspond to a vertical, the spring constant corresponds to a settlement of about 1 inch or 25 millimeters. So that's why you get this 40 factor coming here. And the factor of safety multiplied by bearing capacity of the soil will give you the K value in kilonewtons per meter cube. And when you know the area of the spring, you can multiply this value by the area of the spring, and then it will give the spring constant. So if you want, you can do 2D analysis for box culverts, but on the other hand, you can analyze the box culvert as a 3-dimensional structure as well. So in addition to all these loads due to soil pressure, we have to consider the lateral load due to live load surcharge as well, and the live load surcharge values are given by these. So basically for 30 units of HB, we consider the live load surcharge as 12 kilonewtons per meter squared. And generally the density of soil is considered as 17.6 kilonewtons per, not meter squared, it should be meter cubed. The density of concrete is considered as 17.6 kilonewtons per meter cube, and that's the value that is used in our road development authority in general. So that's a kind of theory. So what I do now is I will show you how to model it using the shell elements, and for that we'll consider one example, and the example is a box culvert with height of 6 meters and length of 6 meters, height of 5 meters, height of 5 meters, width of 6 meters, height of 5 meters. So these are kind of large box culverts used in when you construct expressways, when you want to allow reasonable road, then you might go for something like 6 meter wide box culvert. But if you are allowing 2 lanes of highway, then you might have to go for 7.6 meters. Then you have to go for minimum of 7.6 meter wide box culverts. So those box culverts will be fairly large box culverts. So how you model it is, you can actually use shell elements, and I think this has to be now. So basically you will select one shell element and you can replicate it in all these directions and then replicate the whole thing in that direction. Then you can easily create a model like this. So I'll not spend time creating a model like this because it's very simple. But the other important thing is, when you are doing the analysis, you might need some special arrangement. And here you can see, in addition to the spring, here you can see some restraint has been applied in the horizontal direction. So in addition to the spring, I have applied a restraint here. And if you look at, I'm not sure whether I have applied the same thing here. Yes, I have applied the same thing here, but it's not necessary. But if you want, you can apply at few locations. But other places, I have not done anything. The reason for having a restriction here, the movement restriction here is, if you do not restrain the movement horizontally, then the structure will not be stable. So because of that reason, we'll apply some restraints in horizontal directions, but you don't have to worry about the vertical direction. The reason is there are springs to look after the vertical direction. So then select all this and assign the area section, and the area section is it should be roof, and here you can see it's roof, and also you can see here this flow. That is the flow. And so basically if we do a few simple calculations, so the size of the box culvert is 5 meters of height, 6 meters of width, supported on springs, and then having a road with 0.7 meters of soil fill and 0.3 meters of flexible pavement. And for the pavement, we can use a density of 23 kilonewtons per meter cube. Soil, we will use a value of 18 kilonewtons per meter cube. So you will get a stress distribution like this due to soil pressure. In addition to that, you will get another surcharge like that. Another surcharge like that. So there will be a surcharge like this. The lateral pressure due to soil, and these are the other values. So if you consider that this consists of 5 meter segments, 1, 2, 3, 4, 5. So 5 meter segments like that. Then I can consider the average soil pressure acting at a height of about 1.5 meters. So 1.8 meters. So you get 18 into 1.8 into 0.6. One 1.5 multiplied by 18 multiplied by 0.6, 16.2. So basically we can apply these loads. So due to this load of 0.3 roadway, we get a value of 23 into 0.3, 6.9 kilonewtons per meter square. And here you get 18 into 0.7, 12.6 kilonewtons per meter square. And in addition to that, you get a lateral pressure. And I have considered that, the first element, the height as 1.5 should have been 1.8. So we'll live with that. So here 1.5 into 18 into 0.6 will give you a value of 16.2. And then 1 meter below I have gone for another value. So likewise, I have considered the soil pressure acting at the center, and I have applied that pressure on the element. So you get soil pressure acting from left, soil left,
Hello.
and right.
Yes.
Yes, you want to ask something? Okay, so what I do is stop video. So those are the forces that I'm going to consider. So you will see that
Sure, sure. Can I have a minute, please?
so we can see the forces, loads that have been applied. If you look at soil from top and
Yeah.
gravity, so you can see it has a value, and you can look at one of the elements and consider the load. And here you can see from above, I have considered weight of the soil as 12.6 and weight of the road as 6.9. And then you can also consider the loads on soil left in y direction. And here you can see the loads are varying with the height. And similarly on this side also you can get the loads varying with the height. And then at the bottom, I have not applied any load. You can't see anything called the base. The reason is if you have a load directly acting on the base, it will be transferred directly onto the soil without causing any bending moment. So we don't have to consider any loads that are acting on the base vertically downwards. Whereas, we have to consider the effect of all these loads distributed by the base acting as a raft. So those should be considered. And then you get surcharge left. And surcharge is a constant value. And that is considered as surcharge. And if you look at the loads, consider the point. Here you can see the surcharge is considered as 7.5 kilonewtons. The reason is surcharge is 12 multiplied by 0.6, and that is 7.2, not 7.5, should be 7.2 kilonewtons acting in the lateral direction. So I've entered it as 7.5, should be 7.2. So basically you get loads from this side, loads from the soil. But how about the loads from due to the surcharge? Sorry, loads due to the vehicle movement. And those also should be calculated. And if you see what are the loads, and we see what is the road HB, and that is in gravity direction. Here you can see the weight of the vehicle has been applied as 2 patch loads, and these are span in direction of the box culvert, not this one. These are span in direction. So I have considered that the vehicle is moving this way, and then I have to apply it at a place where that will cause the maximum effect. Then there's a small theory that will help us to find where to apply. So we'll have a quick look at that. So if we consider, so what happens is we have this HB loading, that is highway B type loading, acting over 1 meter width. So this is 261 millimeters. And then you will get another 500 millimeters here. And the spacing between two loads is 1 meter. So you get 4 wheels like this, 1 meter spacing. So as far as those loads are concerned, you get overlap. So here you get overlap. So you can say the total width of the loads with four wheels will be 3 meters plus 3000 plus 261 plus, for 1 meter thickness you get 500 millimeter dispersion, 500 on this side, 500 on this side. So you get altogether 4261 millimeters. And I have created the model by considering a grid of 2, 3, 4, 6. I have considered a grid of 0.5 meter by 0.5 meter. I have considered a grid of 0.5 meter by 0.5 meter. I have considered a grid of 0.5 meter by 0.5 meter. Right? So basically, I have considered this is approximately equal to 4.5 meters. That is so the width of the HP vehicle will be 4.5 meters. And then, yeah.
Sir, how did you get that 261?
Yes, 261 is 75 kilonewtons is the wheel load divided by 1.1. Take the square root of that, and that is 261. Because the contact pressure is limited to 1.1 newtons per millimeter squared due to a concentrated load. Right? So to limit the contact pressure to 1.1 newtons per meter squared, when the load is 75, you can divide that by the stress and then take the square root, then you will get the answer as 261. Is that clear?
Yes, sir. Clear.
Yeah. So you get 261 and dispersion. And then if you consider the other direction, then we have this at 1.8 meters. And we have one moving this way, moving that way. So basically, you will get 1.8 meters, and so you get about 1 meter here, 0.5 meters. On this side, you get another 0.5 meters. And I think I have considered this as equal to 1 meter. So you have 4 wheels, 75 into 4, divided by 4 and 1. So you get 75 kilonewtons per meter squared load acting due to this 75 kilonewtons per meter squared acting on it. So if you consider the model, so you'll end up with Here you can see I have considered the width of 1 meter and 2, 4, 6, 8. I have considered a width of 4 meters. And if you consider the magnitude of the load, live load, I have considered something like 75 kilonewtons due to HB loading. 75 kilonewtons due to HB loading. Then you will ask, where are we going to place these loads? And then again, we have to see where we are going to place this. So there's a theory that is used when you are designing anything with 2 wheels. And the theory is to get the maximum effect, place the load in such a way that one wheel and the resultant of these two loads, one wheel and the resultant of these two loads are equal distance from the center. Equal distance from the center. So these are equal distance. So that means, one wheel has gone past in the center, not at the center, it has gone past in the center. So that the resultant and that wheel are of equal distance from the center of the beam. So that means I should not be placing the wheel here, right on the middle, because then the other wheel will be somewhere here. So I'll consider that one wheel has gone past in this center and the other wheel is here. So the distance between two wheels is 1.8 meters. So I'll consider for convenience 2 meters. If it is 2 meters, then this will be 1 meter. So I have to consider that if this is the center line of the slab, then one wheel has gone passing it and the other wheel will remain behind it. So that's how I have applied the loads. So here you can see, if you look at the loads have been applied in such a way. Here you can see there are 4 cages on this side. Here you have only 3 shells. So I have considered that this is the center 2, 4, 5, and the load has gone passing the center. Load has moved passing the center by 0.5 meters. So that the resultant will act somewhere here. Resultant will act somewhere here. The load will act here. So that I will automatically get something close to the maximum. Something close to the maximum. To get the maximum effect, I have not applied the load right at the center. So if I apply the load right at the center, this load will move somewhere here. Then the effect of this load will be less. To get the maximum effect, I have applied the load. Just pass in the center line. Just pass in the center line. So center line is here. The center line of the center of the load is here, and the resultant center is somewhere here. But I have come closer to the real situation. Not exactly, but I have come closer to the real situation. So with all that, I can create the load combinations. So you can see load patterns. We have the basic loads like the weight of the structure, HB, soil top, soil left, soil right, surcharge, the weight of the road and all that. And then I have the combinations. Combinations like combination 1, 2, 3, and service combination is also there. So the combination 1, here you can see dead load has a factor of 1.15, and we have to multiply it by 1.1. So the dead load has a factor of safety of 1.15, but I told you that we have an additional factor of gamma F3, which is 1.1. So that overall factor of safety will be this multiplied by 1.15 multiplied by 1.1. Then for the weight of the road, I have considered, although it's 300 meters, I have considered it as 1.75 factor multiplied by 1.1. I can actually use 1. If the thickness of the road is less than, is more than 200 millimeters, I can actually use 1.2 as well, but I have used 1.75. Soil at top has a factor of what's in the note? Is it wrong? Soil at top has a factor of safety of 1.2. So it has a factor of safety of 1.2 multiplied by 1.15 multiplied by 1.1. Yeah, that's how you get 1.518. And so here you can see, 1.2 multiplied by 1.5 multiplied by 1.1. 1.15, 1.2, 1.1. Yes. So if I share the note, now you can see the note. Here you have to get 1.2 multiplied by 1.1 multiplied by beta factor, which is 1.15. So you get 1.15 multiplied by 1.2 multiplied by 1.1. So here also you should get 1.15 also into the scene, which is 1.75 multiplied by 1.1 multiplied by 1.15. So altogether 2.21. So here you should be getting 2.21. Then soil left, the factor is 1.5 multiplied by 1.1, which gives you 1.65. So you can see the factors are 1.65, and HB loading, the factor is 1.3, and we have to multiply it by 1.1, you get 1.43. So this gives the maximum on everything, So get 2.21. Then let's look at combination 2, which is the next combination. Here you can see that, we have the minimum load here, but these are kept maximum. So here you can see dead load is 1.265, but road, soil top, all are 1, others are 1.65. And then we have combination 3, where this should be 2.21, but the soil from above are all maximum, but these are minimum. And the minimum value is 0.2. So when we calculated, we use a value of 0.6. So to convert it to 0.2, I have to multiply it by 0.3. So here you can see soil left and soil right, I have multiplied by 0.33, but soil road and soil above kept at a maximum value. So as HP loading. So as HP load. So this is a case where the anything from above maximum, anything from sides minimum. So with those three combinations, we have gone for an envelope. And in addition to that, we have a service combination as well, where all these values are considered as one, and that is to see what's going on with the foundation, or just to see whether the soil pressures can become excessive. Then the other important thing you have to consider is the soil springs. And here, if you look at any location, side joint, and assignment, and you can see I have applied a value of 2000. The reason is the bearing pressure is considered as 100, and then we get a factor of safety of 2 multiplied by 40. 40 into 2 is 80, multiplied by 100 is 8000. And if you consider the area of each spring, it is 0.5 meters by 0.5 meters. So 0.5 by 0.5 by 8000 is 2000. But when you are coming to the edge, the area reduces, so I have considered it as 1000. And when it comes to the very corner, it reduces to 500. So I have considered it as based on area. And with all these, then we can run the analysis. Before I run the analysis, any questions you would like to ask?
Excuse me, sir. Can you please explain that again? How did you locate that loading in the pink color?
Yes, the loading I showed you that, showed you that there's a theory. The theory is center. If you have two loads, the loading is not due to one axle, but due to two axles. So this W, then what is the resultant? Resultant is 2W. So theory is, make sure if you want to get the maximum effect, this load is X distance, one wheel has already gone passing the center line, the resultant is behind, so that the distance to the resultant and distance to the load both are the same. So if I draw it clearly to the scale, like I'll get here I'll get the resultant, get the other load W. So which means I have this loading. I considered that the distance between two loads is 2 meters, and I also considered that this load will be dispersed over 1 meter. Although it disperses more than 1 meter, I consider it as 1 meter. So I have considered 0.5 meters here, 0.5 meters here. So if you look at the model, you will see that I have applied the load in such a way that now if you look at the plan view, here you can see 2, 4, 6. Now this is the center line. This center line, and I have considered that actually there's a small mistake. So I have considered 2, 4, 6. So this 5. I have considered that this acts here, at the center line, and then the centroid should be 1, 2, 3, 4, somewhere here. But if I consider the actual loads at 1.8 meter, if I apply if I consider that the center is here, then it's too far. Because of that reason, I have considered that it acts at 1.5 meter. Otherwise, if I have considered 2 meters, then I could have actually applied this one shell on this side. But what I have done is, because the actual spacing is only 1.8 meter, I have considered only gap of 0.5 meters here. So here I get one loading, and this is the center. The center of loading is here. The resultant will be somewhere here. So resultant is behind the load, behind the center line. This is the center line. 2, 4, 5. This is the center line. Oh, this is the center line. Which one? 2, 4, 6. 2, 4, 6 here. This is the center line. So the resultant, this axle is 0.5 meters ahead. Resultant is behind. Not exactly 0.5 meters, less than 0.5 meters. But resultant is behind. The load is, the one axle is ahead. And this is the center line. Can you understand that? But I have
Yes.
considered one less because the actual spacing is 1.8 meters. If I consider 2 meters, then I might get a lesser bending moment, right? Because I have considered a shell size of 0.5 meter by 0.5 meter. If I have considered a shell size of 0.45 meter by 0.545 meter, then I could have actually 0.45 by 0.5 meter. Then I could have actually applied it exactly. But I have considered a shell size of 0.5 meter by 0.5 meter. Another thing I want to tell you is, because can you remember we talked about haunches? So if you have a haunch, you can actually have thin elements here and then represent the variation of the thickness of the shell element also. That's also possible. You can indicate the variation of the shell element by having thin elements here with different thicknesses. That's also possible. Then what you do is, you can analyze the structure. Then you will get the results. So when you are looking at the results, you have to be again careful. So display. So if you want, you can just look at combination 1, M1 and M22. Now 1 is in X direction, 22 is in the other direction. So we say 22. And if you look at the moments, the values, here you get something like 264, and here you get a value like what is the value? 265. And then you can consider combination 2 as well. Combination 2, not that critical, because combination 2 is a minimum case. And then you will go for third window and display combination 3, 2, and again you'll get a higher effect in the top slab. Here you can see it will get a higher effect. And if you look at the stresses here, these elements, those go up to about 902. And if you look at the stresses here, it goes up to higher than that. The reason is, here the top load is maximum, side load is maximum, all are maximum. So you get that. And then, generally we look at the envelope, that is the combination, and then you have to be careful. So it's a maximum value. So here you get maximum value, 349. But if you look at this element, here you are not getting 190 something. What is the reason? So always when you are looking at the envelope, you have to look at the maximum value and minimum value. The moment you look at the minimum value, you are getting something close to 190. So what you have to keep in mind is when you are doing designs, especially when you are looking at when you are dealing with shell elements, when you look at envelope, always look at the combinations separately as well, to see whether you are looking at the right values. And always don't remember to look at the maximum value and the minimum value. And once you know the moments, you can easily do the designs. And also we look at the 2D view, it's at 0, and display joins the envelope, and you can see the results. Each spring is carrying a load of like 33, 32, and 33 over a load of 33 over 0.5 by 0.5. So you can see the bearing pressure is about 1.132, but this is the ultimate value. So if you want to get the service value, you can ask it to display not the envelope, but the service combination. And you can see it's about 21, 22, 23. So value like 23 divided by 4, multiplied by 4 gives a value close to 100. So basically the bearing capacity is 100. And when the box culvert is designed due to the action of raft, we are getting a uniform pressure under the box culvert, almost uniform, which comes to about 100 kilonewtons per meter squared, and that is the bearing capacity of the soil. And 100 kilonewtons per meter squared is not a very high value, but with that value, we can actually have a reasonably large box culvert. So, any questions on this? Any questions? And then you can design the reinforcement as for BS 5400 part 4. but the difference is there the crack width has to be limited to 0.25 millimeters, not 0.3 millimeters. So you have to actually calculate the crack width and show that crack width is limited to 0.25 millimeters in highway structures. So any question you want to ask? Or is it clear?
Yes, sir.